So this question asks us about using a capacitor to produce a flash of light. The circuit below can be used to produce a flash of light from a lamp with a fixed resistance of 128 ohms. We're given a circuit diagram here with some values. We have the voltage. We're told that there's an internal resistance, little r here. And we have a capacitor with a known capacitance and two open switches. Okay, switch 1 is closed and the capacitor charges up. Calculate the charge stored in the capacitor when it's fully charged. Okay, we're given the voltage that we're using to charge it, and we're given the capacitance, so we just use Q, the total charge, is equal to CV, which is equal to C is 125 times 10 to the minus 6, and V is 12. Okay, so we can work this out. 125 times 10 to the minus 6 times 12 is 1.5 times 10 to the minus 3. Okay, 1.50 times 10 to the minus 3 coulombs. Okay. The internal resistance R of the battery is 1.80 ohms. Explain why the charging is almost instantaneous. Okay, so that's going to have to do with a time constant. Remember we said that a capacitor is fully charged when 5 time constants have passed. So if we can show that the time constant is really, really short, we can say why the charging is almost instantaneous. So the time constant for a capacitor is RC, which in this case is 1.80 times 125 times 10 to the minus 6. So let's have a look and see what that is. 1.8 times 125 times 10 to the minus 6, which gives us 2.25 times 10 to the minus 4. 2.25 times 10 to the minus 4 seconds. Then we'll say it takes about 5 time constants for the capacitor to be effectively charged. And 5 tau is equal to, so this times 5, 1.125 times 10 to the minus 3 is 1.125 times 10 to the minus 3 seconds. And we'll say this is a very short time. It is effectively instantaneous. Okay, cool. Let's look at the next one. Switch 1 is opened and switch 2 is closed, so the capacitor discharges through the lamp. On the graph below, mark values on the axes and plot a curve with at least 3 points to show how the charge in the capacitor changes during the discharge process. Okay, so we want to know the initial charge. In fact, we worked that out in A, didn't we? So the starting charge is 1.5 times 10 to the minus 3. So 1.5, it's probably easiest if we make that here. 1.5 times 10 to the minus 3 coulombs. And we want to work out what the new time constant is because it's discharging through the bulb. The bulb has 128 ohms resistance. So we'll work that out here. So tau is equal to RC, which is 128 times 125 times 10 to the minus 6. Which gives us times 125 times 10 to the minus 6 is 1.6 times 10 to the minus 2. 1.6 times 10 to the minus 2 seconds, or 0.016 seconds. So, and we want to show at least 3. So why don't we make 1.6 2 of these? So 0.016. And then we'll make this one 0.032. And we'll make this one 0.048. Okay, so that's our 3 time constants. Now we need to work out what the voltage is going to be at each. So let's put a little point here, because that's the starting point. And this is going to be 1.0 times 10 to the minus 3. This is going to be 0.5 times 10 to the minus 3. And it's discharging. So V at 1 time constant is equal to 0.37 times 1.5 times 10 to the minus 3. Times 0.37. Oops. Why is this not? Okay. Is 5.55 times 10 to the minus 4. And then V at 2 tau is 37% of that. So let's just go times 0.37 gives us 2.05 times 10 to the minus 4. 2.05 times 10 to the minus 4. This is it. Oh, sorry, this is not voltages, this is charges. Q. And this is also Q. And this is in coulombs. That's in coulombs. And then we'll do one more. Q3 tau is 7.59 times 10 to the minus 5. 7.60, sorry. 7.60 times 10 to the minus 5 coulombs. Okay, now let's plot these points here. So at 0.016, which is 1 time constant, we have 5.55 times 10 to the minus 4, which is just a little bit above this one, which is 5 times 10 to the minus 4. So it's going to be about here. Let's just zoom in a bit here. And then the next one is 2.05 times 10 to the minus 4. So this is 2, this is 2.5, so it's just close to 2 here, just there. And then the last one is 7.6 times 10 to the minus 5. So that's down here. All right, and then we can draw a little curve here. This is going to be pretty rough on my one. Something like that. Okay. Let's just double check these things. We wanted to mark values, plot a curve with at least 3 points. We've technically drawn 4 here. 1, 2, 3, 4. To show how the charge in the capacitor. So we had the charge. We started with a maximum of 1.5 times 10 to the minus 3 coulombs. And we worked out with 37%. So 37%, when it's decreasing, it decreases to 37% of its starting value after each unit of time. And we've got our 3 points, and the graph looks like a reasonable curve as well. Okay, so that's good. Okay, the lamp will glow at a normal brightness if the voltage across it is between 9 volts and 12 volts. Use the graph to estimate the length of time that the lamp is glowing at normal brightness. Okay, so we're going to need to work out what charges those 2 voltages correspond to. So we can say Q is equal to CV. So 12 volts corresponds to a charge of Q is equal to 125 times 10 to the minus 6 times 12, which is we've already worked this out, haven't we? So it's 1.5 times 10 to the minus 3. That's the start. Okay, so it starts off at 12. We want to figure out when it gets to 9. 9 volts is Q equals 125 times 10 to the minus 6 times 9, which is um, 1.125 times 10 to the minus 3 coulombs. Okay, and let's find out where that is on this graph. 1.153. So 1.1 is there. Sorry, 1.125. So it's just about there. So the time is here. So it's going to be if this is 0.0, that's half of 0.16, so this is 0.008. So each of these corresponds to a fifth of that. In fact, what we can see here is that that is about a quarter of the way along. So that's about, this is about 0.006, because it's almost 3/4 to 0.008, right? Okay, so it's going to take about 6 milliseconds. So from the graph, we see that 9 volts will be reached after about 0.006 seconds, or 6 milliseconds. And we have a second identical capacitor connected in series with the one shown. Show that the total capacitance of the two capacitors is 62.5 times 10 to the minus 6 farads. Okay, so C series is equal to 1 over C1 plus 1 over C2, all inverse, which in this case is 1 over 125 times 10 to the minus 6 plus 1 over 125 times 10 to the minus 6, which is equal to 125 times 10 to the minus 6 over 2, which is 62.5 times 10 to the minus 6 farads. Okay. Explain using physical principles the effect of the new capacitor arrangement on the time constant of the circuit. So we can say tau is equal to RC. The new capacitance of the circuit is half of what it was. Thus, the time constant will have Okay, so it says using physical principles, so maybe we should say something about why that's the case. So the lower capacitance means that the capacitor voltage will rise more quickly as it takes less charge to produce the same voltage. Because V is equal to Q over C. Okay, hopefully we've done enough with that question. This is kind of a mathematical reasoning, and this sort of explains why that is the case. It kind of gave us a hint that it wanted us to use some sort of physical principle, so hopefully that's what they were looking for. You can check on the mark scheme.